Hi. Today we're going to continue talking about gas laws, but actually we're going to talk more about liquids than gases. It's just that gases have an impact. As usual, I have a video for you to watch. I want you to write down anything that occurs to you, any good questions you might have. I'll do the talking for him. This is water in a beaker. You can see next to it this large machine. I couldn't quite catch the initial temperature there. Let's say T1. Oh, now I can see. It's about 23 and a half, 24 degrees Celsius. And so we have this, you see this rubber gasket on the bottom. We've got a dish and we've got our beaker and it's got water in it and a thermometer. And then there's this rubber gasket right here. And we have a lid over the top. And I think there's this big machine over here. And that big machine is going to pump air. It's going to pull air, I think, out of this container. And so, let's just watch and see what happens. This is going to be where I need to turn up the speed. Oh, that's weird. Oh, actually, I should slow that back down. That's a little quick. I'll let you know what this sounds like. So that's boiling, actually. That looks like boiling. I mean, I've seen water boil before. Hopefully you have too. Yeah, this water is boiling, and you can kind of see the temperature there. It's still between 25 and... Actually, it looks like it's colder. Yeah, it looks like it's almost level with 20. I'm going to call that 21 degrees Celsius. So that yields some questions, right? So how is the water boiling and you're in between 20 and 25 degrees Celsius, right? What does the vacuum pump do? And why is the water getting colder? It's below 20 right now. I can see that. Yeah, now it's almost down to... Jeez, I'm going to change that. It's almost down to like 16. 17, something like that. That's insane. This one's not necessarily one you could try at home. I mean, if you have a vacuum pump, go ahead and let me know how it works. It's still bubbling. How do you, like it's cooling down and boiling. Like how do you what is this cold boiling magic? I think he's letting the air back in, so we're seeing this condensation start to form as we let the air back in. Yeah, clearly the vacuum's off if you can take the top off. And you can see, oh yeah, that's like below, it's like 15, even 14 degrees. So we've got some questions. We've got so many there. That's a wow. I think one thing I should do is, before I get too much into what's here, we should talk a bit. I mentioned this in our previous video about pressure. And if we've got our little container of water, I guess it's safe to say, as the vacuum pump works, there's less pressure. Well, so there's gas outside and there's gas inside. And so the idea is, as you pump out the gas that's inside, that would yield a lower pressure on the inside. But we're not really worried about the inside of the container versus the outside. That's a hard plastic. We're worried about the pressure on the water. Okay, before we get too far into that, though, I did think some baseline definitions would be helpful. There are three terms that are all very related to each other. We have vaporization, evaporation, and boiling. Vaporization is our umbrella term. Evaporation is the one that you see at all temperatures. So this would be the picture up here, the temperature drops overnight, and the recondensing of the water vapor happens, those clouds, right? But that water vapor came up off the ground and it was hovering there and it cools down and you see the cloud. Boiling is very, very different. We see bubbles and it has a specific temperature. For water, that temperature is 100 degrees Celsius. At that temperature, the particles are moving fast enough to escape the intermolecular forces and become a gas. Except that isn't what we saw in the video. We saw that the boiling was happening around 20 degrees Celsius. And that makes no sense because the particles of 20 degrees Celsius water, that's like a swimming pool, a moderately temperatured swimming pool. Like that's standard room temperature. How do you get water to boil at room temperature? It just like boggles the mind. And to fully explain that idea, we have to talk about a different idea called vapor pressure. Vapor pressure is a result of the fact that evaporation occurs at all temperatures. So with any evaporation, there's always some gas. Any water sample you've ever seen, as long as there's water, a small portion of it is in the vapor phase around that water. Over time, if it's an open container, that's why the water evaporates and fully disappears, because all of it comes out into the air. As that happens, though, that means that some of the gas particles around the water aren't gas. They're not nitrogen, they're not oxygen, they're water. And the contribution of those water particles is what we call vapor pressure. Pressure of a vapor when at equilibrium with the liquid phase. All right, that's a little bit wordy. That's a little bit, these pictures are a little hard to understand, but they are there. That shows how vapor pressure develops over time, and eventually, you got our little barometer set up there. Notice that it's capped on this end. But a better way to think about it is that you have some particles coming from the liquid phase, gas phase back into liquid, some liquid back into gas, but you also have particles that are just like bumping against particles that are trying to escape. And sometimes that bumping will push the liquid particles back down into liquid. It'll slow down your evaporation. And so the way I like to think about it is I kind of approach it from the liquid's perspective, that vapor pressure is a measure of how quickly the particles are escaping. How many of these particles are making it out, and how much are they pushing up into the gas phase. So if you want to think about vapor pressure as a push to become a gas, that might be a good conceptual way to keep it in your head. Which then, now that we have that to work with, brings us back to this discussion of boiling. Because I don't know about you, I can kind of put this together, this idea that as temperature increases, there's more vapor, and the particles are moving faster. So those water particles are going to be moving around a lot faster, and they're going to be escaping into the gas phase more, which means that the vapor pressure, the pressure due to the water vapor, will keep going up, and eventually you're going to get to a point where there isn't really any air above your hot water. It's just all water vapor. And so there's no air pushing down on the water. And if there's no air pushing down on the water, there's nothing to stop it from becoming a gas. All the particles are moving fast enough and they leave. And so taking this push and putting it together with this idea of temperature, our boiling point definition is going to be the temperature when the vapor pressure of the liquid, right? The vapor pressure is pushing up equals the pressure of the air pushing down. If the vapor pressure was greater than the air pressure, then you wouldn't have liquid, you'd have a gas. If the vapor pressure is less than the air pressure, well, then you have a liquid and it's not boiling. But when they're equal, that's when the bubbles start to form and we get the gas spontaneously happening. So you know what that looks like. We have the pictures before. There are some ways to get that to happen. The first way to get something to boil would be to heat it up. That's the one we're familiar with. What I have here is a graph of the vapor pressure of water as a function of temperature. And you'll see this number from before, 760 millimeters of mercury. That's right about here. And the temperature at which the vapor pressure of water is 760 millimeters of mercury is 100 degrees Celsius. So there you go, right? Like that's why the boiling point of water is what it is. That's where the vapor pressure of water equals the outside pressure. So one way to get something to boil would be to heat it up, increase the temperature. Another way to influence how you observe boiling would probably be to use a different substance. If you used not water, it would have a different boiling point. Rubbing alcohol has a different boiling point. Mercury, a different boiling point. I guess vegetable oil, if you wanted to boil it, would have a different boiling point. And that's because the particles have different intermolecular forces, and that affects this vapor pressure, which we'll see on our next slide. And then one other way to affect the boiling point would be to, well, we talked about the bottom, but what about the top? If we reduce the air pressure, Well, that means that the vapor pressure doesn't have to be as big. If we say removed 25% of our atmosphere and we only had 600 millimeters of mercury, then our boiling point would be, oh, I don't know, about 92 degrees Celsius. That would make sense, right? Now we can kind of calculate if our temperature was 20 degrees and you saw boiling in that video, you can kind of guess what the vapor pressure was, because that's where they're equal when boiling happens. So our pressure inside that vacuum chamber was really low. It looks like, based on this graph, it's like less than 50, maybe 30 millimeters of mercury. That's almost a complete vacuum. So that's another way to get it. And if you've ever done any baking, or you've been made pasta before, and you read the directions and it says something about higher altitudes and more time, this is exactly why. If you go up a mountain, if you go up into higher altitudes, there's less air pushing down. The pressure is lower. And as the air pressure goes down, the temperature for the water to make that vapor pressure goes down. You can see if we went down to 600 millimeters of mercury, your water would only boil at 92 degrees Celsius. So if you're cooking something, it's not going to cook as fast because the boiling is at a lower temperature. So to bring this all together and to use our reference tables, the reference table provides 4 different curves for vapor pressure. We have 4 liquids. One of them you should be very familiar with. This one is the active ingredient in vinegar. This is drinking alcohol. And this one is nail polish remover. They have other names, but we're not going to worry too much about those other names. But as you can see, each of them has a different boiling point, right? That when they cross that 101.3 kilopascal line, we did transition over to kilopascals. We see a different temperature down the bottom. And again, we've got water sitting pretty at 100. But then we've got the ethanoic acid and the ethanol and the acetone sitting at different temperatures where they boil. Acetone, it looks like, boils here at, well, these are every 5 or so. It's like 56 degrees Celsius. That's a really low boiling point compared to water. Which, if you remember, we talked about boiling point as a function of intermolecular forces. So this tells you exactly what happens as intermolecular forces change. The vapor pressure changes, and that changes the boiling point. And so looking at this, which of these has the highest boiling point? Well, we could just read across the bottom, and it's going to be ethanoic acid. Now, I did say at any temperature because I shouldn't have said any temperature. That should say pressure. I could say any pressure because as the pressure increases or decreases, you can just imagine that dotted line sliding up or down. Where the dotted line intersects the solid line is the boiling point. So even if the boiling points go up and down, the lines don't cross over each other. So at all pressures, ethanoic acid is going to have the highest boiling point of these 4 liquids. Which of these substances have the weakest IMF? Well, the weakest IMF is going to be the lowest boiling point, so that's going to be propanone, also known as acetone nail polish remover. So that's our relationship. Low boiling point, weak IMFs, high vapor pressure. You can see at any given temperature, too. We can do the opposite. We can draw a dashed line to say this is the vapor pressure at given temperatures. You can see that propanone has a very high vapor pressure compared to the others at any given temperature. So there's your relationship. High vapor pressure, low boiling point, weak intermolecular forces. And then one other way we can interpret this is to use your graph to, you can use the graph to tell the vapor pressure at any temperature, the temperature at any vapor pressure. You know, you can go back and forth with this. So what is the vapor pressure of water at 50? So here's 50. We're going to trace up until we find water. We're going to go over here and estimate. So that's about 30. I would say that's probably 29 kilopascals. If we could zoom in or get closer to the screen, it does look like the line goes slightly under 30. And this is another one of those cases where the Regents is going to say, well, plus or minus 1. They'll give you a little wiggle room, but not a ton. So let's say 29 plus or minus 1. I think maybe the Regents would have said 28 plus or minus 1, but that looks pretty close to 30 for me. And then at what temperature does ethanol have a vapor pressure of 75? So 75 is going to be right here. Let's trace our way over to ethanol. We're going to be right there. We're going to trace ourselves down. And it looks like our temperature is going to be, you know, slightly between 70 and 75, but it does look like it's closer to 72. It's a little bit closer to 70. So let's say 72. Again, plus or minus 1. But this is how we use our table. So to wrap things up, vapor pressure has a bunch of definitions. I like to think of it as how much the vapor is pushing to go out and become a gas, right? Because pressure is a push or a pull. You can increase the vapor pressure of your liquid by either having a liquid with low intermolecular forces or increasing the temperature. And then the boiling point brings in that idea of air pressure. And so either you want to increase your vapor pressure until it meets air pressure, or you want to decrease your air pressure until it meets vapor pressure. You know, two thoughts come to mind after all of this. One, that means if you were in a pure vacuum, you can't have a liquid. Because eventually the pressure would get so low that no matter how cold the liquid is, its vapor pressure would be non-zero, because I don't think you can have a zero vapor pressure. So yeah, if you were in a pure vacuum, liquids don't exist. That's why there's no liquids in space, I guess. And there's one other thing that's still in the back of my head. So what's the deal with dry ice? How do you not see a liquid, right? We just said why liquids exist. So then how does sublimation occur? Because I'll say this, even ice, water, can sublime under the right conditions. Things to think about. If you have an answer, put it below in the comments or ask me about it in class. Thanks for watching.